Today I'm going to speak about gas reservoir engineering. It's a very interesting topic, and hopefully we can gain a lot of knowledge from this presentation. The outline is as follows. First, I will do the introduction and then gas volumetric, and then we will discuss about gas material balance, gas well deliverability, and lastly, I will close by liquid loading in gas wells. Okay, we start by introduction. I take it from Energy Information Administration from America. It is about natural gas. And we can concentrate on this statement. So natural gas has many qualities that make it an efficient, relatively clean burning, and economical energy source. And also, we can read here, burning natural gas for energy results in fewer emissions. Okay? And then the clean burning properties of natural gas have contributed to increased natural gas use for electricity generation and as a transportation fuel for fleet vehicles in the United States. Okay, so what I want to stress here is that natural gas is actually better compared to oil. This chart here, I take it from IEA again. This is the CO2 emission from natural gas compared to that of oil and coal. So we can focus on the light purple chart, and you can see that CO2 emission in gigaton of not coming from natural gas is smaller, significantly smaller compared to that of coal and oil. All right. So if we, as you can see, currently we are facing a difficult situation. A lot of people seems to be like maybe they see oil and gas energy as not very clean energy. Okay, but as we can see here, natural gas can be seen as a clean energy, clean and efficient energy. So maybe natural gas will have a better future compared to oil. And it means that if we want to continue in this path as a petroleum engineering student, petroleum engineering professionals, maybe we can now learn to focus on natural gas engineering, gas reservoir engineering, and gas production engineering. And also, if we look at the natural gas outlook, we can see here in this chart, we have three scenarios: rapid scenario, and net zero, and business as usual scenario. If you want to know the definition of rapid and net zero and business as usual, you can see in this source. But what I want to mention here is that if we go like currently we are consuming the natural gas, we can see that the consumption of natural gas will always increase at least until 2050. So the demand of natural gas is still big, at least until 2050, which means that hopefully there will be more job vacancies for petroleum engineering, concentrating on natural gas exploitation. All right. And then also, if we go with the rapid scenario, yeah, the demand is still high. But if we go to net zero, as you can see, the demand will be significantly smaller. All right. But what I want to emphasize here, there is still future for natural gas. All right, and also for gas production growth by region, we can see that a lot of countries will still produce natural gas at least until 2050. Okay, we can see here the natural gas production from US, from Africa, from Middle East, in China and Russia. And Russia, for at least until 2035, they will still produce gas at a big part, at a large part. Okay, and also this is an interesting chart. We see three scenarios: rapid, net zero, and business as usual, and change in gas demand by sector. I just want to focus more on hydrogen energy, the light purple one. Hydrogen energy is considered as a renewable energy. Okay, maybe you already know that, hydrogen energy, but it is very interesting that to produce blue hydrogen, to produce the renewable energy, so-called hydrogen, it actually takes natural gas, because the raw material to produce the hydrogen is actually natural gas, which means that if you want to produce hydrogen at large amount, we still need to drill wells for our gas, right? So I think, yeah, we can conclude that our future as a petroleum engineering student and petroleum engineering professionals is still quite bright, at least in gas areas. All right, so that's why this is very important. And also you can see a lot of outlooks, maybe from British Petroleum or maybe from Exxon, like the one on the left here. It's 2019 outlook by Exxon Energy, and they forecasted that at least until 2040, the natural gas demand will increase linearly. Okay, and this is the scenarios from our country, our beloved country. We also do three scenarios: business as usual, and PB or pengembangan berkelanjutan, sustainable growth, and rendah carbon. But you can see the gas here. The gas here is shown by the blue chart. Yeah, we can see that the demand for natural gas is still maintained. Okay, obviously in business as usual, and even in rendah carbon or in low carbon scenario, we still produce natural gas at least until 2050. And you know, in 2050, maybe we already old. Okay, so our pathway to 2050 is still, hopefully it will be bright for all of us. Okay, so hopefully this material, this webinar today will be beneficial for us to prepare our way to be expert in this area. Okay, we start then with gas volumetric. Okay, gas volumetric, we want to know the hydrocarbon in place. So this is the conceptual image of our gas reservoir. We know the area, the net to gross, the porosity, the initial water saturation, and then the formation volume factor for gas. I use O here for oil, but I should change it with G. All right, so BGI. And then recovery factor. So maybe you already learned it in your class. It's quite easy. We can know the gross rock volume and net bulk volume, pore volume, and lastly, hydrocarbon in place. All right. It is quite similar with the oil reservoir. So we need to know area of the reservoir, the thickness, and then the net to gross, and the porosity, initial water saturation, and then formation volume factor. So this is the formula, and we need to know about it. Okay, we need to remember this, right? So this is a simple formula to know the OGIP or original gas in place. It is proportional with the area of the reservoir, thickness of the reservoir, the porosity, yeah, and then divided by the BG. And BG can actually calculate with this formula. And then to know about how much gas we can produce, we can actually do this a simple calculation. So gas produced equals to initial gas subtracted by remaining gas. And we can determine the remaining gas if we already decide the abandonment pressure. The abandonment pressure is the last pressure of our operation. Okay, if the abandonment pressure is reached, then we can conclude the operation. We can shut down everything, and then we can close the field and give back to the government. All right. We continue with the discussion of the estimate oil ultimate recovery. It's quite easy. We already know the hydrocarbon in place, and to know the estimate oil recovery, we just need to estimate the recovery factor. How much gas can actually be produced from the reservoir? All right. So recovery factor is actually very important, and this is actually the main responsibility of the reservoir engineers. They need to do their best. They need to create a lot of programs, a lot of activities, drillings, workovers, stimulations, and something like that, in order for us to get as high RF as possible. And for typical values for recovery factors in gas reservoir, for high permeability and volumetric reservoir, we can reach up to 90%, depending on our abandonment pressure. In low permeability reservoir for volumetric, it will be more challenging. So maybe we can produce up to 60%, depending on our well spacing. And if we have gas reservoir with aquifer, water drive, it will be quite challenging. And maybe we can produce up to between 50 to 70%, depending on the aquifer strength and our production rate. You can see also here the data for gas condensate reservoir. Okay, but in this particular presentation, we just want to focus on gas reservoir. Okay, we continue. Now we want to know about the gross rock volume, because we want to know about the gas in place. So if we start from here, we have this schematic of a reservoir. Let's say it's a gas reservoir, and we can divide the reservoir to some segments from segment 1, 2, 3 to n. Okay, we can actually break down the segment to be represented by area and thickness, right? Because area times thickness will be the volume. Okay, so this is actually done by our friends from geologists. It's not done by petroleum engineers. So this is particularly the main responsibility of geologists. But as engineers, we need to know the logic behind the calculation. So after the reservoir has been segmentized by like this one, we can actually calculate the total gross rock volume. Okay, we can do trapezoidal rule, or we can also do pyramidal rule. Okay, so you know here, you can see here delta VB, which is the delta of the bulk volume. So if we sum all of the bulk volumes, we can obtain the total gross rock volume of our reservoir. Okay, so that's one. We need to know the volume of our reservoir, the gross rock volume. But it's not done yet. We need to define, or we need to know about our net to gross, because we cannot actually produce all our gas from all parts of our reservoir. Our gas and our oil is only concentrated on segments that we call the net pay. Okay, like as you can see here, if we have gross rock here with total thickness of Hg, is actually composed of shale and sand and tight sand, and then shale again, sand, and so on and so forth. We cannot actually produce our gas from the shale layers, right? So we need to subtract all the shales, all the water layers, and all the shaly sands in order to obtain our net pay. Okay, so if you can see here, we have three pays. Net pay 1, and then pay 2, and then pay 3. That's actually the source of our gas. Okay, we only produce our gas from the net pay segments. Okay, so if you already know the pay, the thickness of the pay, we can calculate the NTG, or net to gross from pay. This is actually the responsibilities of our friends petrophysicists. Okay, it's not done by petroleum engineers. Okay, luckily, it's done by our friends petrophysicists. So to calculate about gross rock volume, it's done by geologists. And then for net to gross, it's done by petrophysicists. And later on, we will work together to calculate the gas in place. After we already obtain the gross rock volume, the area and then thickness, and then we obtain all the data like this one. The area, we take that data from seismic, thickness from log, porosity, initial water saturation, and net to gross from log, or we can also analyze them from core. BGI, or formation volume factor for gas, We take that from PVT laboratory, or we can also do correlations. RF, we do this by calculation, by analysis, or by simulation. This is actually our main responsibility as petroleum engineers, especially if you are reservoir engineers. So this is the main area of reservoir engineers. Okay. So that concludes our gas volumetric. It's not done yet. We need to compare the results, the gas in place results from volumetric with the method which is known by material balance. This is actually the expertise of reservoir engineers. So later on, we need to compare the result from volumetric with the material balance. If they go along together, then it means that our analysis is right. It's true. It's correct. But if they differ significantly, maybe we need to revise, or maybe we need to revisit either the volumetric one or material balance one, or both of them. Okay, the gas material balance is quite simple. Okay, so we do mole balance here. NP is mole of gas produced, Ni is mole of gas initially, and Nf moles of gas remaining. Or you can also call P for produced, I for initial, F for final. Okay, so NP is Ni subtracted by Nf. Okay, so this is the conceptual model. We start with a tank here. Okay, so we imagine our reservoir as a tank, okay? So initial mole, it's easy. We do this like PV divided by ZRT. Okay, it's taken from ideal gas law. Hopefully you can remember that. All right. So this is the initial moles of gas in the reservoir. Okay, we start with initial reservoir pressure, and we assume isothermal operation so that the temperature is constant. And the volume of the body of the reservoir also assumed constant, V, and then temperature T. Let's say we have water influx, we have aquifer. So the net water influx will be WE minus BW and WP. We produce the gas up to GP and the water up to WP. All right. And then the mole of gas produced should be calculated with this formula. Okay, again, it's PV and RT, but V here is GP. Okay, and then the other is in SC, which is standard condition. Okay, so after we divine this case like this, we can calculate the final or the remaining moles of gas in the reservoir, NF, which is calculated by this reservoir, by this formula. And then we continue, we obtain this relationship. Okay, maybe you can predict where we will go after this. Okay, after obtaining this equation, we do some assumption. Let's say, in general, dry gas reservoirs can be classified into two categories: volumetric reservoir and then water-drive reservoir. In volumetric gas reservoir, we don't have aquifer. Okay, so the reservoir can actually be considered as a closed tank without interference from external source like aquifer. It's only a tank containing gas. Okay, that's called volumetric gas reservoir. And for this type of reservoir, this relationship holds. All right, PG divided by T, this one. Okay, the assumption, volumetric reservoir and no water production, no aquifer, no water influx, only gas. By this assumption, we can derive this mathematically so that we can have these two formulas or these two correlations. P divided by Z equals to PI ZI minus M, which is M is a constant, times GP. Also, we can change it to this form. Okay, after obtaining this formula, we can construct the very important chart for reservoir engineers, which is P over Z analysis. Okay, so if you plot the P over Z result, yeah, you can obtain the P data from static bottom hole pressure data. If you have that, right, you can collect it monthly or bi-monthly or yearly. You can obtain that, and then you can calculate your Z factor, and then you plot it like this one. Let's say we have 6 data in the early time of our production, and then we achieve like this one linear relationship. Okay, this is true for volumetric reservoir, gas volumetric reservoir. So after we obtain this linear relationship, we can simply forecast it. We do linear extrapolation down to 0, all right? And by doing that, we have OGIP, which is original gas in place. How to calculate our ultimate recovery? Well, we can do that by just assuming our abandonment pressure. If you define already your abandonment pressure, you can just draw on your line here and then go down. You get GP in or on abandonment time. Okay, so it's actually very easy for us to do this analysis compared to oil reservoir. Okay, you just need to take your pressure data, reservoir pressure data, or static bottom hole pressure data in timely manner, monthly or yearly, and then you calculate your Z factor, and then done. Also, you have to plot P over Z against the produced volume of gas. Okay, so far so good. But if we have water drive reservoir, it will be more complicated. Okay, so the line or the profile will be deviated. It will deviate to higher GP. Okay, strong water drive, we go with this profile. Moderate water drive, we go by this line. And weak water drive. Okay, so if you have aquifer influencing your gas reservoir, it will be deceptive. It will deceive you. You think like this one. If I do this manually, you think if you see the line here, then maybe you can do forecast until this one, right? You can do this forecast wrongly, like this one, because the data deceive you. If you have a strong water drive, or maybe if you have moderate water drive, you can forecast it to be like this one. It's wrong. That's why we need to know about the aquifer. Okay, we need to know about the aquifer. We need to make sure whether or not there is aquifer, there is water influx, and we need to take a lot of data, especially pressure data. And then we do simulation. Actually, I want to show you about the MBAL simulation, but maybe I can do that later on. I just need to complete this presentation first. Okay, so this is actually easy and interesting. You can construct P over Z analysis if you have sufficient data. So far, so good. Okay, and then we continue with gas well deliverability. Okay, it's still the responsibilities of petroleum engineers and reservoir engineers. Okay, hold on a second. All right, continue with gas well deliverability. We start with flow regimes. Okay, if we discuss about IPR or nodal analysis or gas well deliverability or reservoir performance, don't just go directly to IPR or VLP. That's wrong. That's not a correct approach. We need to first start by flow regime. Okay, that's why I start with flow regime here. So if we have gas reservoir here, it's a radial reservoir, and you can see the reservoir boundaries here. Okay, let's say we have a producing well, at the center of the reservoir. It is producing. And while it is producing, it creates pressure wave, all right? It's like if you throw a rock, a pebble to a pool filled with water. If you throw it to the bottom of the pool, it will create pressure wave, and the pressure wave propagates bigger and bigger and bigger and bigger, all right? It's the same thing if we produce the reservoir. It creates disturbance. It creates pressure wave, which will propagate bigger and bigger, like this one. Until at one point, all right, it touches the boundaries, all right? It hits the reservoir boundaries, okay? At this condition, we can say that pseudo-steady state flow regime is reached, okay? We are now in a pseudo-steady state regime, okay? And then we can also plot it like this one. If you have your well producing at QG, the gas flow rate, we start with initial reservoir pressure. This is the external pressure. We produce, we create drawdown, and then we have bottom hole flowing pressure here. So the pressure wave or the pressure trend will be like this. If we reach pseudo steady state flow, okay, we have boundaries. The radius of the reservoir is RE. Okay, this is the radius of our well bore. If this is true, if we reach this condition, then we can calculate our gas flow rate. Okay, so we need to be careful. There are actually three flow regimes in the reservoir: transient, pseudo steady state, and steady state. Okay, we need to use the equation rightly. Okay, we cannot use transient equation within the pseudo steady state equation. Okay, so this formula is true for pseudo steady state flow. Okay, so the flow rate of gas is proportional to permeability and then thickness, and then this one is pseudo pressure. Okay, and then it's divided by temperature, logarithmic natural of RE by RW, and then minus constant, and then plus skin value. You know this already, okay? So this is actually the equation after we reach pseudo steady state flow. But we're not yet completed. You can see here, this is changing. The pseudo pressure is not constant, it's changing, so that we can actually separate the terms like this one. Okay, we take permeability, thickness, and the other to the left side, and then we can concentrate on the pseudo pressure. Pseudo pressure is actually defined by this equation. So it's integral from PWF to average reservoir pressure of this one. Okay, we can recall pressure divided by rho Z is directly proportional to 1 divided by rho and BG. Okay, so we can actually concentrate on this one. We can isolate this pseudo pressure. I'm gonna use pointer. Okay, this one. Okay, so we can also say it like this. This one is actually the same with this one. This one is actually proportional with this one. So you can use this form 2p divided by rho z, or you can also use this form. And then we can plot it. This term plotted against pressure. If we plot it this way, we can observe three regions: low pressure region, medium pressure region, and then high pressure region. Okay, we can focus on each region. First, region 1, the low pressure region. It's actually, by some expert, it is below 2000 psi. In this region, we can observe that this term and this term plotted against pressure, it gives linear relationship like this one. It's linear, okay? Which means it will be easy for us. It's not curved, okay? For us, mathematicians or scientists or engineers, linear relationship is easy, right? It's very easy, but it will be more challenging for curve form like this one. So below 2000, it's linear, and the rho g times z factor, it's constant. Okay, using this one, you can change the pseudo pressure to be this one, the pressure square. We don't need to calculate about the pseudo pressure. Okay, right? It's a painful thing to do to calculate about this pseudo pressure, because it involves integration. It's not that easy for us to do integration, right? But if we can change the pseudo pressure to pressure square like this one, it will be much easier. Okay, provided that you have the data, the reservoir pressure data, and then flowing pressure data. Okay, and then what about between 2000 and 3000? Okay, we face the curvature here. Okay, it's not easy. We cannot run away from this situation. And in this region, we cannot do approximation. We have to use pseudo pressure. If your well is operating between 2000 and 3000 psi, unfortunately, you have to use, or you have to calculate the pseudo pressure. But most softwares, most commercial softwares can easily convert your pressure to be pseudo pressure. So it's not that big problem actually. It will be challenging if you use spreadsheet or Excel, because you need to do the integration there. Okay, but if you use commercial software, it's easy. It can be converted right away. Okay, so between 2000 and 3000, if you want to calculate your gas flow rate, you have to use this formula. Okay, you need to know about the permeability. You can ask the petrophysicist again for thickness. You can ask the petrophysicist. Temperature, you can do the measurement. Okay, RE, or the radius of the reservoir, you can assume. Okay, or maybe you can analyze that, you can predict that by pressure transient analysis or well testing. RW, the wellbore radius, you can ask the drilling engineer, and you have to know the radius of the wellbore. And skin, you can predict that. You can do pressure transient analysis. It's easy, provided that you have all the data. And lastly, above 3000 psi, we know, or we can see that 1 divided by rho times B plotted against pressure, it's constant. Okay, so it's actually easier. The pseudo pressure can be approximated by just pressure. No need to pressure squared, no need to do pseudo pressure. You can actually use your pressure data. Okay, so if you are producing a well operating at or above 3000 psi, you can use this form. All right, so to just do a brief recap like this one. Below 2000 psi, the approximation is called p-squared approximation. This is the form. Or maybe you ask, what is DQ? DQ, it's actually non-Darcy flow. It is additional skin due to turbulence, but we will not discuss it in this presentation. Okay, so yeah, you can take it, or maybe you can just neglect the DQ if you assume laminar flow. But most of the time you cannot do that assumption. we need to calculate this dq. Okay, but you can study or you can learn about it later. And between 2000 to 3000, we cannot do the other way. We need to do, or we need to calculate the pseudo pressure by this one. And then about 3000, we use this formula. All right, so far so good. But sometimes it is too complicated, too many parameters to be considered, right? And for engineers, especially if you are field engineers, we are not really comfortable with too many parameters, something like this one. So maybe, and most of the time we do not analytical like this one, analytical or theoretical. We do empirical, right? And it is much simpler. The empirical method says, which is with CNN method, one of the most popular formula, it says that the flow rate of our gas well is equals to C, which is a performance coefficient term, times this term. Okay, so reservoir pressure squared subtracted by flowing pressure squared, and then all of them powered by n. Okay, n is exponent, and represents the turbulence effect. So using this method, you can honor the turbulence effect. Okay, it represents the turbulence effect, which is the additional pressure drop due to high velocity of gas. The turbulence at the sand face area, okay, near your wellbore. Use n equals to 0.5 if you have turbulent flow, and n equals to 1 for laminar flow. Whereas C, the performance coefficient, it accounts for reservoir properties, fluid properties, and reservoir flow geometry. So everything here, K, H, T, rho, Z, and then RE, RW, is actually contained by this parameter, this C, which makes everything better for us, right? Okay, so for my beloved Indonesian friends, if there are some things that are very unclear in Q&A session, you can ask in Indonesian. Okay, so that's not a problem. Okay, so this one, we start from this equation, and then yeah, just do some logarithmic calculation. It turns to be log Q equals to log C, and then N times this one. By this one, we have linear form or linear relationship. It makes things simpler because we can do like this one, okay? Provided that you have maybe at least three data or four data, you can plot it like this one. So on the horizontal axis, we have flow rate, and on vertical axis, we have pressure term, whether pressure squared or pseudo pressure or pressure, okay? So if you do well testing, you can open choke opening 1. You measure the flow rate, you measure the pressure, and then you increase the choke, and then you measure again. You get Q2 and pressure 2. And then you open your choke again, bigger one. You have Q3 and pressure 3. And lastly, you open it for the final time, okay? You have Q4 and pressure 4. If you have this one, you plot it, you can see a linear profile like this one. Then you're almost there. You can calculate your N like this one. You can calculate your C by this formula. Okay, so this is actually the CNN method analysis, but we can obtain the data by doing some well testings. Okay, there are three types of tests you can do. First, back pressure or flow after flow test. Okay, so first you open the first choke. Okay, choke 1. you get on the upper chart, it is actually pressure, and then below chart is flow rate. Okay, so first choke, we have flow rate 1, and then we measure the bottom hole pressure by our pressure gauge. Okay, and then increase the choke again. We have this Q2. We have this one. Again, increase the pressure, increase the choke, and then finally until the fourth data. Okay, you do this by the well testing, but the condition is the stabilized rate and stabilized flowing pressure has to be reached. Which means that the well should reach or should approximate the pseudo steady state condition. Okay, we cannot do transient regime here. We need to achieve pseudo steady state regime. Okay, to know how long should we flow our well, we need to use this stabilization time formula. It's actually time required to reach pseudo steady state condition. All right. This is not a difficult formula. If you have porosity and the other data, then you can easily calculate your stabilization time. But if the stabilization time is too long, for example, if you have low permeability reservoir, most of the time TS will be very, very long. And we cannot do back pressure tests. Okay? So we can substitute the test with isochronal tests. Okay? So it is quite faster. So you need to open your well and then shut in. Okay? Open it again, bigger choke, shut in again. Open it again, shut in again. Open it again, shut it again. Okay? The short flow period should be of equal duration. So the flow period should be of equal duration. Usually it is from 4 hours to maybe 7 or 6 hours of flowing pressure. And then the shut-ins should be of equal duration until stabilization. So you still need to reach stabilization or pseudo steady state flow condition for your shut-ins. Okay, but the flow duration not necessarily equal with shut-in duration. That's the condition for isochronal tests. Okay, but the data is the same. You need you obtain your flow rate, you obtain the pressure. All right. Lastly, to make it much faster and much simpler, we do modified isochronal tests. Maybe this is the most popular and most practical to be done in the field. Okay, so you need to flow, shut in, flow, shut in, flow without reaching stabilization. Okay, again, I need to mention that stabilization time means that the time required to reach pseudo steady state condition. Okay, you already noticed about the pseudo steady state condition previously. Okay, where the pressure wave hits all the reservoir boundaries, and it takes quite a long time. Okay, in modified isochronal test, or MIT, it's not Massachusetts Institute of Technology, all right? It's modified isochronal test. It's faster. Okay, so if you have 4 flow periods, it means that you obtain 4 data, right? And again, you plot it like this one, or you can also plot it like this one. This is in the linear form. This is in the original form. Okay, but the result is the same. You obtain the absolute open flow or maximum gas flow rate. Okay, this is actually your gas well performance or gas well deliverability. And if you are reservoir engineers or petroleum engineers or production engineers, this is actually, this analysis should be your priorities, maybe on daily basis, because your boss, your manager will always ask how much gas flow rate we can obtain from that well. And then what about that well? And what about the other? And then we need to do a lot of well testings, which is fine. provided that we have all the measurements, we can obtain all the data, we have the right softwares. All right, so far so good. We already discussed the introduction, gas volumetric, gas material balance, and then gas deliverability. And then lastly, oh, not yet. So if we know already the deliverability of our reservoirs, the production system is actually like this one, okay? You have your reservoir here with all the pressure terms, reservoir pressure, delta pressure for skin, flowing pressure, delta pressure for tubing. This is actually the friction pressure, okay, for tubing and for skin. Wellhead pressure, flow line pressure, separator pressure, suction pressure, and discharge pressure from the compressor. So this is actually the gas production system, okay? If you know this system, then we can then construct the IPR-VLP relationship like this one, okay? We obtain this IPR from well test, all right? So we have constructed the IPR from well test, either from back pressure, MIT, isochronal test, whatever. Okay, we get the data, we construct the IPR. And then we construct also the VLP. But in this presentation, I will not discuss about the VLP because it is a bit more complex, okay? A lot of iterations here and there. IPR meets the VLP, we have the operating rate. If we have low permeability reservoir, the trend should be like this one. You will have a skinnier IPR. In this one, you have a fat IPR, okay? IPR yang gendut. Di sini IPR-nya menjadi lebih kerucut, lebih kurus, because we have low permeability reservoir. The same if we have skin, okay? If you have skin, if you have low permeability, the IPR will be like this one. It will be skinnier. It will be thinner. This is for IPR. And then we discuss about not yet. Lastly, about the lower reservoir pressure. If you go to below reservoir pressure, then your IPR will be suppressed like this one. You will be shorter, but it's quite different with low permeability. Okay, you can see here, right? This is just a concept, okay? In the real world, we need to do the simulation. And then, what about the VLP? We finish the IPR, then VLP. Starting from here, if we have higher wellhead pressure, higher system pressure, or smaller choke, or smaller tubing, or high water gas ratio, then you will go up for your VLP. But that's not in a good way, because if you go up, it means that your gas flow rate is lower. Okay, so if you have higher wellhead pressure or higher system pressure, you will get lower flow rate. Okay, so your system pressure should not be that high. Okay, and then if you decrease your choke opening, or if you use smaller tubing, or if you have water gas ratio higher, yeah, you will get this one. You will get lower flow rate. All right. Okay. I actually want to show you also about the pipe sim, but I will do later on if we still have if we still have time. I will close the presentation with liquid loading in gas wells. Okay. This is very important. This is actually not the expertise of reservoir engineers. This is actually the responsibility of our friend production engineer. So if you want to continue from student to be production engineer, then in gas field, then one day you need to discuss about liquid loading. Okay, so what is actually liquid loading? The definition: liquid loading is the inability of a produced gas to remove the produced liquid from the wellbore. Oke, jadi gasnya nggak mampu mengangkat liquid dari wellbore, so that one day the gas well will die. Okay, reasons: gas rate below critical rate, reservoir depletion. You have lower reservoir pressure. Okay, you have water condensation, you have free water production, or you have water conning, and it makes your hydrostatic pressure higher. Okay, it will make your produced fluid, the weight becomes increased. Okay, and then bad completion design, high wellhead pressure. Okay, as mentioned before, don't use too high wellhead pressure. Okay, what's the impact? Loss or no production at all. Okay, your well will die. You can also create formation damage or water blocking, and then of course corrosion. So the concept is like this one. First, you have a healthy well, a healthy flow condition like this one. You have annular flow. Okay, your gas are concentrating on the center part of your tubing, whereas all the liquids flowing on the wall. Okay, I continue. But if our reservoir pressure decrease like this one, the pressure keeps decreasing. Okay, the flow regimes within the wellbore also changes from annular flow to slug flow, plug flow, churn flow. I will not discuss about the flow regimes in this presentation. Okay, so you can learn by yourself about plug flow, slug flow, churn flow. It's actually like this one. Okay, lastly, before you die, I mean before the well dies, I'm sorry, it reach bubble flow, and it's undesirable because the gas well will die. It's just bubbling up rather than flowing like this one, annulus flow. Okay, this is stable flow. For annular flow, going to plug flow. Okay, but in slug flow, you will create slugging. Okay, we don't like slugging because it will give impact to our production system. Okay, it's unstable. Again, it's stable flow, but it's stable for the liquid because the gas flow rate will be too low, like this one, until it dies. Okay, decreasing gas rate with decreasing reservoir pressure, starting from annular flow, ending with bubble flow, or ending with no flow at all. Okay, I've mentioned before that one of the reason is gas rate below the critical rate. So what's actually the critical rate? Okay, this is the theory. We can calculate the critical rate by do this balance. So in this annular flow, we have gas at the center of the tubing, whereas there are droplets of liquid like this one, also in the center of the tubing. Okay, so we have the dominant phase is gas, and then the minor part is liquid droplets. This is the liquid droplets. It will move by drag force. Okay, force go higher, go to the top, but it will drag down by the gravity. Okay, so it goes down to the balance between the gravity force and then the drag force. If gravity force wins, then we will have liquid loading. Okay, but if the drag force wins, then we will go up. The well will be healthy. But if they are balanced, if the gravity force equals the drag force, then we have status quo. We will not die. We will be relatively healthy. Okay, gravity force and then drag force. Okay, so we just do need some mathematics. It's not really that difficult. Okay, so yeah, maybe we can also neglect neglect everything, and then we just focus on the critical flow rate. All right. This is the equation to calculate the critical flow rate coming from the Turner velocity. Okay. This is one of the most popular equation for determining the critical rate. Okay. One day when you do a final assignment, maybe if you analyze the gas well, one day you will see Turner equation. Okay. From Turner, we go to flow rate. Okay. The formula. You can see it's quite easy, right? So if you want to calculate the critical flow rate, you need to know the pressure. You need to know the volume. Okay. Oh, I'm sorry. P is velocity. Velocity coming from the above. You know, you need to know the area of the tubing. It's easy. Area of the tubing, right? Luas tubingnya. And then you need to know the temperature, and then you need to know the Z factor. Okay, it's easy. If your flow rate, if your actual flow rate is higher than critical flow rate, then everyone's happy. But if your actual flow rate is smaller than critical flow rate, then it's dangerous because you will face liquid loading. Okay, you need to do the calculation at all the sections of the wellbore, not only on the wellhead, not only on the bottom hole. All right, so you need to do simulation using wellbore model. Okay, like this one. The red line represents in situ flow rate, whereas the green one represents the critical flow rate. Oh, I'm sorry, it's the other way around. It's the critical flow rate, it's the in situ flow rate. So on the left profile, we see that our actual in situ velocity or flow rate is higher than the required critical rate. So it's healthy. This one, it seems good from the wellhead down to the packer, because the green line always on the right side of the red line. Okay, but this is where we need to be careful. Below the packer, we will see casing, or we will see annulus. We will not see tubing. We will see a wider area, and in that way, the critical flow rate is below. I'm sorry, the in situ flow rate is below the required critical rate, and we will have liquid loading on the bottom. On the upper side, we can see that we are healthy, but on the bottom, our liquids load up. That's the analysis for our critical flow rate. Okay, maybe this is the last one. I'm sorry. Okay, last one about the diagnostics. Where we observe these phenomenons, it shows that our gas well is load up. Okay, if we see fluctuating gas production, liquid production stops altogether, it's one of the symptoms that our gas well is suffering from the liquid loading. And then if we have liquid slugging at the surface of the well, and if you see the wellhead pressure, you see the casing pressure is relatively constant, but your tubing pressure is spiky like this one. It's also a symptom or a sign of a liquid loading phenomenon. Or if you do a flowing pressure gradient, you plot it to be like this one. You see the change of the gradient from a low gradient to high gradient. It's also a symptom of liquid loading, because the low gradient represents the gas zone, okay, whereas the high gradient represents the liquid zone. Okay. Also, if you have sharp drops in production decline like this one, it means you have liquid loading. Okay. The normal trend, the normal decline should be like this one, but your production is erratic, naik turun, dan akhirnya ngedrop. It is also a symptom of a liquid loading in gas well. Also, if you do, or if you plot your IPR VLP, if you obtain your production operating rate here, it means you are healthy. But if you have the cross section is on the left cross section or left part, it means that your production is unstable. You are producing on unstable zone, and maybe most likely it is affected by the liquid loading phenomena. Lastly, if you produce to and measured by orifice meter, okay, if you see like spiky looks like this one, it means that you have liquid loading. Okay, you have sluggings, you have slugs of liquids, and that's why it becomes spiky. Okay, that concludes my presentation.
Okay, thank you for Mr. Richard. We are going to the next agenda. The next agenda is question and answer session. If you have question, please turn on your camera and turn on your microphone. You can directly ask for Mr. Richards. Or if you have back connection, you can text your question on checkbox. Okay, guys, hello everyone. Who wants answer? Who wants asking for Mr. Ricards? Do you have any question for Mr. Ricard? If you wanna ask in Bahasa, it's okay. Or if you are from abroad, you can ask by using English.
All right. Assalamualaikum warahmatullahi wabarakatuh. My name is Adrian Saputra. I'm from Islamic University of Riau. I want to ask you, sir, I have some question. And for the first, talking about gas, there are many companies that don't use gas to sell. They only sell oil. And why is this happening? Even though this gas can be used, and for example, for household. And second question is, on your slide, there are some material such as gas material balance and something else. Are all this calculation done in one project, or it is just the method we are needed?
Okay. Shall I answer directly?
Yes.
Okay, thank you for the questions. First, let's say we are an oil and gas company and we only produce oil. Why don't we also produce gas? The first and the easiest answer is because in our wilayah kerja, on our operating area, we don't see any gas field. Okay, if we do exploration and we don't find any gas reservoir, then we cannot produce or we cannot exploit or we cannot produce gas. That's the simple thing. But sometimes in oil reservoir, we have gas cap, we have associated gas, and in some operations they don't also sell the gas. Why? Because maybe they want to use their gas for gas lifting. Okay, if you want to do gas lift for your oil operation, then you extract your gas, you inject back to the reservoir through the wells, through the gas lifted wells. That's why we some of the operations, some of the companies don't sell gas. But the easiest is because they don't have or they don't own a gas reservoir. And then for material balance or gas well testing or gas deliverabilities, all of the analysis actually is not something that like they're not the same. You have to do both of them. Okay, if you have a gas reservoir, it means that you need to construct gas material balance. You need to construct P over G analysis. Okay, maybe you need to do decline curve analysis or even reservoir simulation. Okay, but if you have completed the material balance analysis, it doesn't mean that you don't need to do the gas deliverability analysis. You still need to do the analysis. Okay, you still need to do well testing, because material balance is only focused on knowing your production forecast or gas in place, whereas gas deliverability is focusing on the health of the gas well. So they are not the same. Okay, gas material balance is telling us the gas in place, telling us the forecast of the reservoir, whereas gas deliverability tells us how much gas flow rate you can produce from your particular well. Okay, thank you.
All right, thank you, sir.
Thank you. Okay, sir, we have a question for Jack. The question is from Irfan from Indonesia Open University. Dear Mr. Richard, how may increase well gas performance with chemical? So if we well gas production drop, what must inject chemicals?
Okay, if I may, I will use Indonesia bahasa. Okay, for Mr. Adrian. Oke, ini saya beranggapan chemical untuk liquid loading. Oke, sometimes if we have liquid loading, jika kita punya liquid loading, salah satu obatnya adalah kita inject surfactant. We inject chemical. Why? Because ketika kita masukkan surfactant, ya biasanya soap stick namanya ya, kalau bentuknya padat. Istilahnya itu kayak kita menjatuhkan sabun ke dalam sumur. Oke? It's like we dropping a soap stick down to the wellbore. Oke, ketika si chemical ini, surfactant ini mixing dengan water, water yang ada dalam wellbore, dia akan membentuk busa, bubble. Oke? Ketika dia jadi bubble, densitasnya itu lebih ringan dibanding ketika kita punya hidrostatiknya water. Oke, jadi teman-teman ngebayangin tekanan hidrostatik, kalau sumur kita tubing itu penuh dengan air, itu akan berat. Si gas itu nggak mampu untuk mengangkat si water. Tapi kalau kita inject chemical dan dia mixing, dia ngejadi berbuih. Itu sama kayak Coca-Cola. Kalian kocok-kocok, dia bisa keluar gitu dalam bentuk buih. Sama juga sumur seperti itu. Gitu ya. Jadi betul ada kita injeksi chemical gunanya untuk meringankan beban liquid di dalam sumur sehingga akhirnya gas mampu mendorong si liquid tersebut karena kita sudah bikin dia jadi busa. Oke, itu biasanya surfaktan bisa kita dalam bentuk liquid, kita injeksinya batch gitu ya. Kita turunkan kayak coil tubing, bukan coil tubing. Intinya capillary tubing, kita teteskan gitu ya, kita masukkan chemical, kita masukkan surfaktan ke bottom hole, atau kita masukkan bentuk sabun, bentuk stick gitu ya. Kita drop, nanti dia creates bubble, jadi ringan, lama-lama kita bisa ngalir gitu. Tapi kadang-kadang kebanyakan seringkali sumbernya mati lagi gitu ya. Jadi harus kita drop surfaktannya secara kontinu. Gitu ya. Thank you Irfan, Mas Irfan Adrian.
Okay, Mr. Irfan, it's great. It's done, right? Okay, we have a next question for checkbox. The question is, thanks, Mr. Ricard. It was such a great presentation. Permission to ask, I have a two question for Mr. Richard. In a producing oil, is it we ignore the rate gas or keep calculate both rate oil and gas? The second, which one method gas deliverability to use in a well testing from three methods? After knowing the deliverability some well, what further step are we adjust rate production? Thank you.
Okay. Okay, first, maybe I can use English. Okay, Mr. Basit. In producing oil, of course, the more data we obtain, the better. It will help us to analyze more properly for our well. So if you have oil well, it doesn't mean that you need also only to measure the oil flow rate. You must also calculate or measure the gas flow rate, because it will later on help you on constructing your material balance, right? Material balance in oil reservoir, you need gas data, oil data, all data. If you can obtain, just obtain it, okay? And also the meter or alat ukur, the meter for gas is not actually that expensive. You can measure it with our orifice meter. So yeah, there is no reason, there is no strong reason for us to not measure the gas flow rate, okay? So you need also to measure or calculate the gas flow rate. And then for the second question, which one methods gas deliverability to use in well testing from three methods? I assume you are talking about back pressure, isochronal test, and then isochronal test, modified isochronal test. I prefer modified isochronal test because I can complete the test faster. Okay, I don't need to wait until stabilization. Okay, so you can do the well testing using modified isochronal test. And then if you already know the gas deliverability, let's say you already know the gas flow rate, you already know the absolute open flow, and what you need to do then after that? Yeah, it depends on your operation requirement. Okay, if your contract, right? So your company is having a contract with a buyer company. Okay, maybe PLN atau perusahaan pupuk, they buy your gas. Okay, if their demand increase, then you need to increase your gas flow rate. Kita buka coknya lebih besar. Okay, but if they do shutdown on their plant, jadi misalnya pabrik bayarnya itu shutdown, mereka maintenance shutdown, yeah, then we don't need to produce our gas. We just need to decrease the gas flow rate, or maybe we can close our well. Okay, so after you know the deliverability or the performance of your gas well, okay, then yeah, you just need to adjust your flow rate as required sebagaimana diperlukan oleh operation. Kalau penjualannya ingin naik, kita buka gasnya lebih tinggi. Kalau penjualannya lagi turun, kita turunkan coknya. Jadi seperti itu ya, Mr. Basit. Thank you for your question.
Okay, Mr. Basit, it's done right. Okay, last time I looked at Miss Rahmi Nurul raise the hand. Okay, for the Miss Rahmi Nurul, please turn on your camera and your microphone to ask directly for Mr. Richards.
All right, thank you, the moderator, for giving me a chance. So before that, my name is Rahmi, and I'm from a student of Islamic University of Riau. So I'm curious about, when you're talking about vertical gas well, I'm curious about how to calculate the IPR, or inflow performance relationship, of vertical gas well with varying skins.
Oh, That's very good question.
Yeah, I'm so crazy.
It's more complicated. We need to, yeah, actually, wait. So yeah, first you need to plot your skin versus your flow rate. Okay, so you need to create another plot, which is Q versus skin. So if you have Q1 flow rate 1 versus skin 1, and then you increase your flow rate, you have Q2, you get skin 2. You then get Q3 and then skin 3, and then you have the correlation, and then so that you can obtain this term. After knowing that relationship, you can then obtain this DQ. Okay, so you get that this DQ term from that analysis, Q versus skin. Okay, using this relationship, you can then adjust your flow rate based on your skin. Jadi misalnya kita naikkan Q-nya, skin-nya akan bertambah sehingga Q-nya akan terkoreksi oleh this term. Okay, so it's actually is not that simple. We have another discussion for that. We need to do specific discussion about that. But this term gives the way for that discussion. Okay, this non-Darcy flow term. Okay, this is actually the friction term because of the changing skin. Okay, this term is because of the variable skin. Okay, hopefully you can learn it because unfortunately I cannot present that right now. Thank you. That's a very good question.
Thank you so much for your answer, sir.
Yeah.
All right. Can I ask one question?
Of course. Yes.
All right. My last question. You already talking about liquid loading before, right? So it really catch my eyes. And my question is, are there some actions that can be taken to reduce liquid loading?
Okay. If you want to do to reduce your liquid loading, okay, wait. Liquid loading. Okay. So it's actually we can look at this one. Okay. If you want to decrease your liquid loading, okay, it means that you need to lower your critical rate. Okay. If you decrease your critical rate, okay, if you decrease your critical rate, maybe you can have a better operation. So one way to avoid liquid loading is we use smaller tubing, because if we have smaller A here, okay, smaller A, it means that our required critical gas will be smaller. Okay, jadi so if we have small critical rate, it means that maybe our actual rate will be higher than critical gas rate. Okay, so one way is to reduce the area by using smaller tubing. Also, using the smaller pressure. Okay, if you have smaller pressure here, it means that your required critical gas rate is also smaller. So don't use too high a wellhead pressure. Jadi jangan wellhead pressure terlalu tinggi. Jangan choke itu terlalu kecil. Because if we use small choke, it means that our wellhead pressure will be high, so our required flow rate critical will also higher. So there are a lot of ways we can decrease or we can limit our liquid loading. For example, using operating at a lower wellhead pressure, or using smaller tubing, or increase your choke opening, or maybe you can inject surfactant like I said before, inject surfactant, or if you already loaded up, okay, then you have to take the water off by using your artificial lift. Okay, so actually artificial lift is not only operatable in in oil wells. It's also can be used in our gas well. Gas lift, electrical submersible pump, PCP, progressive cavity pump, Sackrod pump, all of them can be applied in our gas well to produce the water so that we can avoid the gas production from attacking our well, from making our well dies. Okay, so hopefully that answers your question.
Okay, thank you so much. So can we use flow the well at high speed to stay in the mist flow by using a smaller pipe or by creating a lower wellhead pressure?
Yes, of course. But if your water production is too high, yeah, sometimes we give up. If our gas production is too high, we cannot run away sometimes. But if we still have chance, then we can use smaller tubing or open our wellhead pressure to be smaller. Open increase choke like this one, like that one.
All right.
Thank you.
Thank you. Thank you so much, sir.
Thank you for your good question, Mr. Rahmi. Okay, we have some question for Jack box. This question from Subham PDEU from India. The question is, how do we ensure that the recovery factor that is calculated is not underestimate or overestimate? Which is the best way to forecast the recovery factor, sir?
Okay, the best practice to find the appropriate recovery factor is to use a lot of tools. You need to do reservoir simulation. You need to do material balance. You need to do decline curve analysis, and you need to do the other analysis. Okay, you need to consider all the analysis there are to forecast your recovery factor. And you need to also consider about your well spacing. If your well spacing is too high or too big, you will not get a high recovery factor. So you need to align your production scenario with drilling scenario with reservoir management. And we can also actually look up to the typical value. If you have a volumetric gas reservoir, you can actually expect up to 90% recovery factor. But you need to align that with your drilling program. If you have big reservoir with only one well, you cannot achieve 90%. You need to spread your well evenly, maybe uniformly. You need to pack your reservoir with a lot of wells. But you need to also consider about the economics, right? So there is no easy or direct answer to estimate the recovery factor. A lot of factors influence the recovery factor, like whether or not you have aquifer, your well spacing, your permeability, and then your operation, your abandonment pressure, or maybe your water production, a lot of things. So the only way, the best practice to forecast our recovery factor is to do the reservoir simulation. By considering your drilling program, your workover program, and the other programs like stimulation, or maybe if you have a gas injection or the other programs. That way, you can properly forecast the recovery factor. Thank you, Mr. Subham.
Okay, thank you for your answer, sir. Okay, we have two questions again. We have a question from Cameron. It's too far right. His name is Ibrahim Mazabo from School of Geology in Cameroon. The question I want to ask, what is the best model of water inflow to use for a radial aquifer on MBAL software, sir? What is the best graphical method for history matching?
That's actually a good question. So aquifer has a lot of uncertainties. We cannot know the thickness, the radius, the permeability of our aquifers, right? So actually there is no easy or there is no a silver bullet answer. What is the best model to model our aquifer? But most of the time I see it is a Hurst and Everdingen method to 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 model our aquifer. Okay, if you have you can also use like Carter-Tracy, yeah, or Vetkovich. Maybe these three of them. Okay, Hurst and Everdingen and Carter-Tracy, and then Vetkovich. So if you can do them, that's okay in MBAL software. And the best graphical method for history matching, at least you need to do two graphical methods, P over Z method, and then call method. You need to plot with call plot or call method to analyze whether or not you already predict properly about your aquifer. Okay, so if you already match, if you already obtain a linear term, or maybe a linear term, a linear profile for your call plots, it means that you have predict your aquifer properly. So by doing call plot and then P over Z plot, that's two of the best graphical methods to support your MBAL analysis. Thank you. Hopefully it answers you, Mr. Ibrahim Dabo. Or maybe Ibrahim.
Thank you for your answer, Mr. Richard. Okay, I wanna the people from abroad, it's like from Cameroon or India or the other country, to ask directly for Mr. Richard. We want to know each other. It's not only from checkbox. We want to know each other. Please, from the people from the another country, can you show on your camera and turn on your microphone to ask Mr. Richard directly? I wanna know each other. Maybe there is somebody from abroad here who wants to open the camera and open the microphone and ask for Mr. Richards.
Hello.
No?
Hi, sir.
Hello, sir. I am Ibrahim Dabo from Cameroon.
Yeah, hopefully that answers your question, all right? You can do P over Z analysis and then call plot.
Okay, sir.
Yes.
Okay, thank you.
Yes. Thank you so much.
Or if okay, we are continue for the others question on checkbox. The question from Agitama from Islamic University of Riau. In the case, in a gas well, the water coining has reached the gas zone and has been mixed with the gas. Can the gas still be produced if the possible in that way?
Okay, it depends on the case. Okay, if your water conning is very severe, jika water conningnya itu terlalu parah, the water production is too high, maybe your gas well will be loaded up. Okay, it will die. But if you have suffered from water conning, but your gas flow rate is still high, let's say if you have reservoir pressure that is still high, then you can still produce. Okay, you can produce simultaneously the gas and the water, but it depends on your reservoir pressure, wellhead pressure, and then the tubing, a lot of factors. Okay, the only way to know whether or not you will load up is to do simulation, well modeling. Like if you can use a pipe sim or maybe Prosper, you can do. The parameter that you need to analyze is the WGR or WGR, water gas ratio. Okay, so you need to know, or you need to determine your water production. You need to estimate that, and then gas production. So you have some possible WGR. Okay, and then you do the sensitivity in your software, and then you can see whether or not at a certain value of WGR you will manage to produce, or the gas well will load up. Okay, so hopefully that answers Mr. Agitama. But most of the time, if you have reservoir pressure that is still high, you can still produce. Thank you.
Okay, thank you for your answer, sir. Okay, we have the last question for chatbots. Maybe the next question for directly. Okay, the last question for chatbots is from Habib Rahman from Anna University, India. The question is, what are the major advanced technologies like IOTS alt used in gas reservoirs?
Should we wait for him to open the camera, or should I answer?
I hope Mr. Habib Rahman, can you open your camera and open your microphone? Please, I hope you can. If you have a good connection, maybe you can open your camera and open your microphone for Mr. Habib Rahman. Hello, Mr. Habib Rahman. Okay, do you still hear? Are you still here, Mr.? Hello, Mr. Habib Rahman. Are you still here? Hello, can you hear me? Mr. Habib Rahman?
I can't open the camera, connection problems. Okay, no problem. All right, so I will answer. So actually, we can do many things with IoT, with artificial intelligence, with machine learning. For gas reservoir in particular, the easiest thing, not the easiest, one of the things that can be done with IoT is to predict whether or not you will load up. Okay, so if you have a gauge, let's say on your wellhead, you can measure the flow rate, you can measure the temperature, okay, and then on the station, on your test separator, you also have the monitoring component, or maybe the gauge meter, something like that, and all of them record the data continuously and then send to the computer on your headquarters. Okay, they record the data continuously, and they will determine, they will know whether or not at one point you will face liquid loading. So as you can imagine, they know the wellhead pressure, they know the temperature. You also have already input the tubing, the well configuration, also the flow line configuration, and then the meter, the gauge, measured the wellhead temperature, wellhead pressure, and then the flow rate. So by giving the machine learning or the artificial intelligence testing and the learning, okay, neural network, something like that, it will predict whether or not you will face liquid loading. So that's one example of the IoT. And I think a lot of things can be done with machine learning or artificial intelligence or IoT for gas reservoirs. There's no particular, or there's no significant difference from oil operation. Okay, so in oil operation, you can do that for artificial lift operation. In gas reservoir also, if you do artificial lifting, you can also do the IoT there. Okay, and for gas reservoir engineering analysis, like maybe reservoir simulation, maybe material balance, well testing, everything, most of them can be done IoT. Okay, so hopefully that answers your question, Mr. Habib Rahman. Thank you so much.
Okay, thank you for your answering, sir, and thank you for your question, Mr. Habib Rahman. Okay, maybe this is the last question. I give chance for somebody here who wants to answer, who wants to give a question for Mr. Richard, who wants to ask Mr. Richard. Please turn on your microphone and turn on your camera. Please, everyone who wants to ask Mr. Richards. Maybe somebody from abroad. Yeah, maybe we can sharing each other here. Don't be safe. Everyone, ayo, come on, somebody else wants answer, wants ask for Mr. Richard. Don't be safe to open your camera and open your microphone. You are sharing here each other. Hello, everyone, come on. Maybe from staff SPUSG, do you have any question? Brother Reza Amanda, do you have question, brother?
I think enough.
Okay, enough. Okay. Come on, maybe we have some minutes.
Can I?
Okay, Mr. Rahmi.
All right. Talking about gas reservoirs, before that, thank you for the moderator. And here I am. I am from staff SPURSC, Secretary 2, and my question is the application of hydraulic fracture horizontal well considered necessary to get an economic flow rate in tight gas reservoir?
Okay. So that's a very good question. For hydraulic fracture or for economic analysis, there is no direct or straightforward answer. You need to consider both the revenue you obtain from the production and then the cost you must spend. Okay, hydraulic fracturing is not it's not cheap. It's quite expensive, especially if you have horizontal well. So reflecting on the shale reservoir in US, okay, something like that, they have a lot of horizontal wells in gas shale reservoir, and then they do multiple fracturing. Okay, that's expensive, but maybe they can obtain high gas production from that. So they need to do cost analysis, economic analysis, and they need to review the IRR, okay, rate of return, okay, and payout time, and then everything, all the parameters to know the economics of the project. So you need to do that. But let's say we set aside first the economical discussion and we focus on the technical discussion. If you have a very low permeability, if you have a very tight reservoir, then there's no way there's no way to run. You need to do the hydraulic fracturing. Azidizing most of the time cannot help you. Even doing the horizontal well cannot help you. Most of the time, we need to do hydraulic fracturing. And if you have horizontal well, you can also do multiple fracturings, something like that. So yeah, but you still need to do simulation. Okay, you need to input your permeability prediction. Okay, you need to input your well configuration. You need to input your reservoir pressure, and then you construct the well deliverability curve. You construct the IPR, and then you can decide whether or not you will need hydraulic fracturing. Okay, in hydraulic fracturing preparation also, you need to predict. You discuss with the vendor, you discuss with the technology provider, because we cannot do by ourselves as oil company, right? We need to discuss with them whether or not we can achieve a particular target. Let's say I want to enhance my production up to this point. Is it possible with hydraulic fracturing? If yes, then we can go to the hydraulic fracturing. But also we have to consider about the cost, something like that.
Okay, thank you so much for the
yes.
very interesting answering.
Okay. Thank you.
Thank you, sir.
Thank you for Mr. Rahmi for your question, and thank you for Mr. Richard for your answer. Maybe that's the last question, and I say thank you very much for all of participants who have answered, who have asking for Mr. Richard, and I say thank you very much for Mr. Richard Arnold for all of knowledge and experience. I hope we can use all of knowledge for the futures.